Good morning, everyone. In this video, we'll be starting the last lesson of Unit 3, looking at our last type of transformations, which are stretches and shrinks. So the nice thing about stretches and shrinks is it's still following that pattern that we've been looking at with location in the function versus whether it is a vertical or a horizontal transformation. So if I have a number, let's say a, being multiplied on the outside of the function, so multiplied on the outside, we would say it is a vertical transformation. If we have a number being multiplied inside the function, that's this b value here, so multiplied on the inside, then we say it's horizontal. And I want you to just put in parentheses inside the function, not just parentheses. So inside the function, not just parentheses. And you'll see what I mean by that once we start getting into some of these more complicated problems. Now, you'll notice on this page that I have X'd out or blocked out some of this information. This is just to clean up this page a little bit. We've talked about most of this already with reflections and horizontal shifts. So on this page, I really want you to focus on vertical stretches, horizontal stretches, and the warning down at the bottom. So first we're going to talk about the a value, or a number that gets multiplied on the outside. It's multiplied on the outside. So as usual, our vertical transformations are a little bit more intuitive. It is a vertical stretch if our a value is greater than 0. And this makes sense because bigger value would think of it stretching or getting bigger. So a vertical stretch is when the number is greater than 0. And when we describe these transformation, folks, we're not only going to say it's a vertical stretch, we're also going to state by how much it is stretching. So in this example, if I have 2x squared, that 2 is on the outside of my squared function, so it's not inside parentheses getting squared with the x, so it's 2 times the squared function. So we would say this is a vertical stretch by a factor of 2. And in our coordinate formula, we would multiply all of our y values by 2. Now, the other side of this is vertical shrink. If our number being multiplied is between 0 and 1, which means fractions and decimals, then it is going to shrink by that factor. So for example, in this one, we have 0.25 times our square root of x. So we would describe this as a vertical shrink by a factor of 1/4. And in our coordinate formula, we would multiply, again, our y values, since it's vertical, by a factor of 1/4. So we have to be a little bit more explicit when we are describing these. In Algebra 2, you may have just described these as getting narrower or wider or fatter or skinnier. So we are going to describe it vertical or horizontal, stretch or shrink, and also describing the factor by which it is stretching and shrinking by. So folks, looking at this example to the right, we have our parent function, absolute value graph. And then we have this graph below. Now, as we're looking at that little expression, how many transformations are occurring here? If you're looking at it going, well, it's just negative 0.25, wouldn't that just be one number or one transformation? That negative and the 0.25 count as 2 separate transformations. Notice that for my a values, it never says anything about if a is less than 0 or less than 0 over here. The less than 0 or the negative aspect of this transformation goes back to what we did on the previous page. The negative vertically reflects our graph. So top over bottom, it reflects over the x-axis. Excuse me. Whereas the 0.25, it's on the outside of our absolute value function. So this would be a vertical shrink because it's a fractional number between 0 and 1, so vertical shrink, by a factor, or actually we'll just say by 1/4. So it's by a factor of 1/4. We'll just make it a little bit shorter and say it's by a fourth. And that tells me how much it is shrinking by. So folks, to visualize this, if I look at this parent function v, if I vertically shrink it, it's like I'm pressing down on that v. So pressing it down is going to kind of flatten out the sides of it, as we see here. And since I have also vertically reflected it, that's why it is an upside down V. So for shrinking, think about pressing on it in an up-down fashion and spreading out the sides of that V. All right, folks, so again, the vertical transformations are fairly intuitive. Stretching for numbers, shrinking for decimals and fractions. Where it starts to get messy is with our horizontal ones. So first, horizontal is when we have a number getting multiplied on the inside of the function. And I'm going to go ahead and draw crossing my eyes again. Because similar to how with our sliding transformations, it's opposite direction of what we would think. With this, it's going to be opposite the number of what we think. So I'm going to give you some strategies for how I interpret these transformations. First, I don't use B itself to determine the stretching or the shrinking. What I do first when I see a horizontal number or a number being multiplied on the inside, so for example, this 1/3, I identify it as inside the function, which makes me cross my eyes and do the opposite and reciprocalize that number. So the opposite, or crossing my eyes and reciprocalizing 1/3, gives me the number 3. The 3 is what I use to determine whether it is stretching or shrinking. So I first reciprocalize the number 3, and similar to above, 3 is a stretch number. So I stretch by 3, and that is what I'm multiplying my x values by in my coordinate formula. So folks, I'm going to go ahead and label those steps one more time. The first thing we do is determine that it is horizontal. That's step 1. Next, we reciprocalize that number and turn it to the number 3. Our third step is determining whether it is stretch or shrink. So horizontal, inside the function, we reciprocalize the number and see that it's 3. That is what determines that it is a stretch. So a little bit trickier, just like our other horizontal transformations. So in the similar fashion, horizontal shrinks, if I look at this 2, it's being multiplied inside my squared function or inside my quadratic, so I know that it's horizontal. I reciprocalize that number and make it a 1/2. 1/2 is a shrink number, so that is what I use to describe this transformation. A horizontal shrink by the reciprocal of 2, which is 1/2. So I use the 1/2 in my coordinate formula. Oof. So let's see what this looks like in action. It's kind of tough to tell from this graph, so I'm just going to go ahead and darken my parent function here. There's my cubic function, and here is my transformed function. And let's go ahead and look at this expression and identify our transformations. First, there are 2 different transformations happening here. The negative is on the inside of my cubic function, so that will be a horizontal reflection. And that fits with what our graph is showing us. If I take this cubic function and flip it left to right or swivel it over that y-axis, this swoosh is going to go over there, and this swoosh is going to go over there. So horizontal reflection. Now for the 1/3. We see that it's on the inside, so we know this is horizontal. We cross our eyes and reciprocalize that number to be 3. 3 is a stretch number, so horizontal stretch by 3. So again, those horizontal ones are really quite tricky. Now, down at the bottom of this page, we have this warning. I want you to put a whole bunch of stars by this section because this is one of the hardest things to remember. This warning says that you must factor any coefficient of x within the function before trying to describe a horizontal translation. So folks, what this essentially means is no coefficients of x on the inside. So if I look at this example, we can see that the 4 is going to move our function up 4. And the tempting thing is to look at that -3 and say, oh, our function's going to move to the right 3 units. But because this x has a coefficient in front of it, before we can describe this sliding transformation, we have to factor out that 2 from both the x and the -3. So when I divide both of those by 2, notice that it is still inside my cubic function, but it has changed my sliding transformation to be -3/2 instead of -3. So I have to factor out this coefficient first, and now I'm going to be describing what I see here. As I said, the +4 is going to move us up 4. This -3 is on the, -3/2 is on the inside of our cubic function. So we cross our eyes and it moves it right 3/2. Now this 2, up above, I stated that inside means horizontal, and it has to be inside the function, not just the parentheses. So folks, this 2 is outside the parentheses, but is it outside the function? No, we can see up here that that 2 is inside this cubic function. Same with here, it is inside this cubic function. So it's outside this little parenthesis, but it is still inside the cubic function. So that means this is going to be horizontal. It's being multiplied, so it's either stretch or shrink. We cross our eyes and reciprocalize that number to be 1/2. 1/2 is a shrink number, so a horizontal shrink by 1/2. Yikes. All right, folks, moving on to our next example. And actually, folks, before we move on to that next example, if you're looking at this going, I don't know, I don't really think this is going right 1/2. I really think that saying that it is going right 3 would have been correct. Folks, I have graphed my parent function and this 2x minus 3 plus 4. Oop, I didn't want to put that log there. There we go. And I have done this to show you that when we compare the cubic function, the parent function, to the transformed function, does that central point look like it has slid over 3 units to be here? No, it looks like that central point has slid over 1.5 or moved right 3/2. So again, folks, we're going to be describing these transformations without our calculator, but sometimes it's important to go back to the calculator and just show, yeah, this really is sliding right 3/2, not right 3 units. So this is why we have to be aware of that warning. So now going to our next example. This says 1/2 the natural log of -x plus 4. Now, this one also throws students off because it doesn't look like there's a coefficient in front of that x. But since it is a negative, I have to factor it out from both the x and from that positive 4. So this negative is a coefficient. So when I factor it out, this is the function I'm going to be looking at to describe the transformations. So a minus 4 on the inside is going to move us right 4. This negative, though it's outside the parentheses, it is inside the natural log function. So this will be a horizontal reflection. This 1/2 is on the outside of that natural log function. So this will be a vertical. 1/2 is a shrink number. So a vertical shrink by 1/2. And folks, on the next page, up at the top, we're just going to be putting all of that stretch and shrink stuff together again. Lots of announcements today. So folks, again, don't pay attention to this coordinate formula stuff on the side. I think that is more confusing, which is why I've included these instructions instead. So first, if it is a number being multiplied on the outside, a stretch is when your value is greater than 1. A shrink is when the value is between 0 and 1. For a number being multiplied on the inside, we determine that it's horizontal, then we reciprocalize that number, and we use that number to determine stretch or shrink. Because then the rules still apply the way they do with the vertical stretch and shrink. Now, something to take note of is on my math lab, sometimes they will use slightly different notation. Sometimes stretch will be referred to as expand or expansion, and sometimes shrink will be referred to as compress or a compression. And if you're like, geez, why can't they just decide on one term? It is important to understand that there are sometimes many ways we can describe the same thing in math. So these words can be used interchangeably. So just be aware of that when you see it on my math lab, either on the homework or on the test. So folks, in the next video, we'll start putting all of these transformation rules together and getting some more practice with this trickier inside stretch and shrink transformations.